Welcome to the afternoon session of day one of Quantum. Our next speaker is going to be Aaron, who's right here at CMU in the Robotics Institute. He's going to be talking about Piccolo.jl. So take it away, Aaron.
Yeah, thanks everyone for coming. It was a surprise to me when I found out that JuliaCon was going to be in Pittsburgh this summer. I even was going to try to nominate it, but was distracted by other things and it ended up being here anyway. So I figured since we're in my home university, it would behoove us to do a little bit of history about control. So back in the 80s, the Robotics Institute was founded at Carnegie Mellon with the intent purpose of doing robotics and like pushing the frontier of what you can do with mechanics, physics, modeling, control, computers. This was like a lot of new inventions coming together. So this was back in the 80s. I took this frame from another video, and it was a really good one. There's a lot of these videos. Let's see if this one runs. So ignore this. So there's no audio, so I'm going to try to explain what's going on. This is a hopping robot. This is one of the first robots from the Mark Rabert, who's now at Boston Dynamics. His lab started at CMU in the 80s and then moved to MIT, and he was working on legged robots. And these are all dynamical robots. These are legged robots that are running control online, modeling the system, and doing really cool things. So you see these robots evolving and getting better and better and growing legs. This one has 2. The previous ones had 4. Interestingly, all of these have to be in motion as you do this because static robotics was hard. It is hard, but it's somewhat, in some sense, easier to do things in motion. And like using control methodologies and modern control and computers, they're able to do more and more advanced things. I think this one's going to do a backflip or a front flip. So like this was pretty crazy at the time, and this was like 40 years ago, which is pretty wild. And you can see these things getting more and more advanced. And then after this, in 2007, CMU also made a lot of splash in the world for winning the DARPA Grand Urban Challenge. So this was like self-driving cars. So they actually had the first car to drive across the country, and this was in 2007, I believe. And this was like, we're gonna solve self-driving cars. Obviously, it's kind of not solved. We haven't gotten there exactly yet, but the technologies and then control methodologies, a lot of control methodologies had to be put into making these things work, and computing power. So now, fast forwarding to today, my lab is in the Robotics Institute at Carnegie Mellon, and we work on all manner of different robots. So we do kind of game theoretic self-driving maneuvering, dancing quadrupeds, tiny NPCs, so putting microcontrollers on drones, expanding space structures, a lot of weird kind of drone flying patterns, mimicking stuff with quadrupeds, balancing quadrupeds on things with like reaction wheels. So like modeling a lot of really interesting physics, and getting like the most out of the models and getting the most out of the hardware by leveraging a lot of these confluences of technologies. So like all of this kind of boils down to solving, like you want to do something, like you want to put a satellite in like kind of co-orbit with another satellite to maybe do some sort of docking procedure, and you want to do this thing and you don't want to violate the laws of physics. You also don't want to run into each other or run out of fuel or spin too fast and kill the humans that are on board. So there's a lot of constraints that go into these optimization problems. And in the quantum domain, it's exactly this. So we have like models for our systems. We have Hamiltonians, and these define the dynamics of the system. Typically, we want to do some sort of gate, and we have some control directions, and we have to like coordinate these control directions to be able to realize a gate. And we want to do this as fast as possible. We want to like stay in the computational subspace so you can do error correction and not leak into the higher subspace. You need to obey the hardware and like what the lasers or the control lines can actually do. You want to be robust to error sources, or maybe be sensitive to error sources. Like if you're building a quantum sensor, you want to be sensitive to some specific kind of error. And there's all kinds of other constraints that we've talked to experimentalists about that they want to put on their system. So traditionally, and this goes back to the 80s, is a method called GRAPE, or indirect trajectory optimization, or a shooting method, where basically you say, okay, I have my model, I can simulate it forward with some controls and evolve it, and then I can calculate how bad I did and then back propagate a gradient. So this is what GRAPE does. So if anyone's done any optimal control in the quantum world, and Q-control does this, and there's a lot of software packages for doing this, this is an old trajectory optimization method that robotics has since done a lot of work to do, leveraging high performance nonlinear programming to solve optimization problems that look like this. So previously we're optimizing just over the controls they use, while in direct trajectory optimization you're optimizing over all the states at each time step as well as all the controls, and then you enforce dynamics via constraints. And I've given 2 talks on this package in 2 previous years. So if you're curious about the details of this, I highly recommend searching piccolo.jl, and you'll find 2 YouTube videos where I get really into this. So I didn't want to go talk about how all this works, but it's very interesting. And the short answer is we're using a lot of optimal control theory and numerical optimization stuff to solve these problems more efficiently. So like we've actually started to like play around with a lot of different problems, and like a very simple one is doing something on a qubit, and like just to like kind of quickly demo this in Flow Julia, we drew a Julia logo on the block sphere of a qubit, and like you can see this is the actual control pattern that we're solving for doing this, and we can draw pretty much whatever we want. You can kind of do some pretty wild things, including like, let's say you want to do like different gates. You have some gates you want to rotate about some axis to some varying degrees, so some varying different theta. You can kind of leverage this whole thing and stack all these problems together and get these like gate families. And this is really interesting from like the perspective of doing kind of living in the simplex between like the key gates that we want to implement on a quantum computer, C0, CZs, swaps. So like you can solve these problems in a very efficient way using this toolbox. And then I want to plug some of our recent work. This is in preparation. And basically what we did is we were working on neutral atoms. So we're using one of QR's devices, and we're shining a single laser beam at pretty much all of the atoms that are there. So we're doing global control, and which is interesting because you can't control every individual qubit, but you can still do interesting things. Like in this case, we're trying to do some Hamiltonian evolution, evolve some non-native Hamiltonian about to various taus. So basically do rotations about some non-native Hamiltonian to some varying degrees, and we find these gate families that can do this, and we've shown this on hardware. So this is coming out. I forgot to cite the actual author, but it's Hung-Yi Hu at Harvard, so be on the lookout for that soon. We've also done a lot of stuff with superconducting devices. So to tout one of our recent ones, we solved for this Q router, and this was a complicated problem because we're kind of like modeling a lot of the physics that are going on under the hood, and we're actually trying to solve for these fluxes that could like couple these 2 transmons together. So there's a lot of interesting modeling and constraint work that went into this to solve for effectively the controls and then map those back to the actual fluxes. So our solver, and Andy is the one to ask about this, was able to handle this. And this was a hard problem that involved a good amount of control work to actually get going, as this control problem was quite hard for our current tools. We had to implement things like splines to get this to work. And yeah, just to like kind of like highlight kind of how this direct trajectory optimization works is like, it's maybe like starting your thing with a good guess is really hard. So what direct trajectory optimization allows you to do is say, okay, we have this really hard problem. We can start from like anywhere, and this manifold is like the space of feasible initial guesses. And then a indirect method like Grape has to like traverse inside the space, while a direct trajectory optimization can like kind of hop over barriers and land back in. So check out the previous talks for that. Okay, so now we're gonna see if all the code actually works. So on the left, I have a notebook pulled up where I'm including Piccolo, I'm including Quantum Toolbox, linear algebra, sparse arrays, random. We're gonna define some extra like utility functions that just make things a little easier for down the road. Let's look at a single qubit example first. I'm gonna zoom in here. So in our framework, it's very easy to set up problems at a high level. So let's say you have some Hamiltonian, which is like just so you have a drift term that's z, and you have some drive Hamiltonians x and y. You just basically define these. We have some utilities for defining this. Quantum Toolbox obviously has a lot of utilities for defining this. You define a U goal. So you define a goal state a goal unitary that you're trying to reach. And then we can define, and actually this problem we're doing quantum state transfer. So we say, okay, psi unit is the ground state and psi goal is our U goal operating on the ground state. And I'm going to run this, and then you define this thing called a quantum system with your drift and drives. You define some parameters like how many time steps and what should the time step be. And you, like I said, you just set this up, and then we can solve this. And this kind of rips through, and you can see like pretty quickly we've reached a good solution. We can roll out the fidelity, and you see we've gotten like many nines of fidelity. And then we can pop this up, and we can see like kind of what this trajectory looks like on the Bloch sphere. So you can see we're doing this kind of complicated pattern on the Bloch sphere. That's kind of like like the Z rotation is kind of whipping you around, and it's able to coordinate these drives and land at the one state. So we're doing a bit flip. And like, let's see like how fast this was. You can see, okay, this took 6 units of time. I'm not going to get into what exactly the units are here. And then crucially, another key feature is we can set these things called minimum time problems. So this is like, because we have the ability to put constraints on the states in this framework, we can actually say we want to keep the final fidelity to be some minimum fidelity, in this case 99, and then solve for the shortest amount of time that you can do this gate in, subject to that constraint. So this can totally do this. We can set this problem up, and we can solve this, and it's gonna crank for a little bit, and you can see like it's already basically finished. And then we can animate this Bloch sphere, and it looks a little different. And you can see the duration is about half. So the minimum time trajectory duration over the initial duration is 0.5. So we basically have the time to get and realize this gate. And this works for any numbers, any type of quantum system, any type of problem. It's really nice. Okay, so I mentioned before Piccolissimo. So this is something we're working on. Actually, kind of behind the scenes, we're doing a bunch of under the hood improvements for the speed of these things that we haven't made public yet. So we have this package Piccolissimo, which speeds things up, which I actually had to do in order to solve these problems here, because we're going to switch to bosonic systems. We're going to do some cat state, some bosonic system state preparation problems. So as you probably know, you've probably seen a coherent state. So a coherent state is kind of a superposition of a bunch of Fock states, weighted in a certain way, and then you can build a cat state out of these coherent states. You can build other states out of these coherent states. They're very useful kind of states in bosonic systems for a variety of reasons in a variety of contexts. Okay, so we're going to say, okay, we're going to put 20 levels in our cavity, and we're going to find a creation operator, A, and then we're going to build a quantum system where we're basically have only drive terms. We have single photon operators, we have 2 photon operators, and we have our Kerr nonlinearity. So we can set up this, and then we can say, okay, we're going to build our displacement operator function. Quantum Toolbox and other packages obviously have a lot of this. We're trying to port stuff over from this. So I use some of that here to build a Fock state. And then I get the data of it. So this was a quantum object from Quantum Toolbox. Just to like kind of look at what these things look like, I'm going to build a bunch of like, if I just keep running the cell, I can build random Fock states. So I'm just kind of randomly sampling alpha of the displacement, which is a complex number. And like you can see, like these things are basically blobs that live somewhere in phase space. So on the right, I'm showing the phase space plots from the Wigner function, also from Quantum Toolbox. So then let's do this again. Let's get our psi 0, our ground state. Let's make a psi goal where we go to like 1 plus 1i as the displacement operator. This is basically an arbitrary Fock state. We can let this run, and this is going to, as you can see, be a little slower, and these are bigger problems. But if we let this run, this is going to run for 50 iterations. So as this goes, I'm just going to start running these. I should have ran that before, but I'm going to run these. Okay. So this is going to run for a bit, and you can see, I just want to point out a couple numbers in this output here. So if you use this package, there's two real numbers to look at. The objective, so that's this number here, and this primal. So this is the primal infeasibility. So this is saying like how feasible, how well are the constraints satisfied. So this is the constraint violation. So we want this number to be really low. And you can see we kind of got there. We got down to a rollout fidelity of 92 fidelity. So I'm going to move on from Fox states. I'm going to move on to cats. And this has been running while I ran this. So we're going to make a two-legged cat. And you can see this already finished. And we have a rollout fidelity of 89. So that's not that good. So I only ran for 50 iterations. So let's run it for another 50. It saves the place of where you were. So you can just call solve again. Actually, I lied. I didn't have the solve in this cell. So it's going to start from scratch. But it will save if I go like this. We can run this a second time. And you can see like this is kind of getting close to making a cat. Definitely we can make cats, and let's see how close this gets. Yeah. If anyone has any questions, I can take one now. Otherwise, this will finish momentarily. We can look at what this was. Okay, so this was a 97% fidelity cat. Let's watch the animation of this making it, and we can see like this is getting a lot closer to what we want to see from a cat. It's still a little off. So if we run it for another 50 iterations. Oh, not that one. You're right. Thanks for the hint. All right, we're going to skip ahead to three-legged cats now in the interest of time. So this was all lead up to the star of the show, which is the three-legged cat. So we're going to make this thing called a three-legged cat. I don't know if anyone's seen these states, but they're another type of cat state. You can make any legged cat state, basically. So we're going to set up this three-legged cat problem. I wanted to show off a future here. So this problem actually took a little while to solve. So what I did was I previously saved a trajectory, and it's really easy to load a trajectory. So we have these things called name trajectories under the hood where we store all our trajectories in. There's a package nametrajectories.jl. And I can actually just load in this trajectory. It's just living right here, prob3 trajectory. And you can just load this in, and then it's a great way to initialize the problem. And you can just call save on a trajectory in a path and very easily save these things and load them again with JLD2. So let's call this, and we'll solve this now, just to get a more polished solution. So this had I could have run the fidelity before, but we can run it after. So we can say roll out fidelity, prob3 trajectory, just so we can see what this fidelity is afterwards. Yeah, we'll just let this go for a little bit. So what's interesting about these types of states is that you can do a lot of cool things with them. So there's a number of companies that are like working with cat states to do error correction. So a very cool thing is you'll see like you're kind of moving two coherent states away in phase space. What's very cool is the bit flip error. So switching from one cat state to a zero cat state exponentially decays with how far away you move in phase space, if I have that right. And it's very nice because you're basically trading off bit flip error for phase flip error, which you can correct for with error correction. I'm not an expert on this, but you have these really nice properties of these states that could allow for near-term qubits that are really high quality, and like Amazon is working on these as well as Alice and Bob. And you can do other cool things like you can make sensing states out of bosonic states and sense things like dark matter. There's actually some work that's in progress where you can make states that are sensitive to a certain type of dark matter particle. So there's a lot of very cool things you can do with bosonic states. Okay, this is about to finish up. I spieled for a bit. And bada bing, bada boom. Okay, a few nines of fidelity, and you can see like we're doing a lot of crazy stuff, and we're landing at this three-legged cat state, which I wish I had been able to color properly and make it look the best colors that it could have been. This is work to be done, but it's kind of fun just to watch like how these things come together in phase space and landing at this thing that, as you'll notice at the end, it's this three-legged cat state, which is a very interesting thing that you can just make in these states. And then we can look at also what the pulse is that actually created this, and this is kind of the drive amplitudes of all those control terms. Okay, so now to come back to the slides. Okay, so I mentioned like all these visualization things, so we kind of introduced a bunch of this new visualization tools in a new package called PiccoloPlots.jl. So this is all under Piccolo.jl, which is kind of a meta package that contains a bunch of packages underneath. We also did a bunch of work recently to kind of peel off the core like direct trajectory optimization part of the code to make this like basically general for any direct kind of trajectory optimization problem, including in robotics. We've come to a robotics lab, so people are starting to use this for robotics applications. And we're kind of abstracting all this away and making like direct trajectory optimization really modular. And then adding on different backends. Like we're using IPOps. We want to use some of the stuff from the SciML ecosystem, and also a talk on Friday that I'll be giving on trajectory bundles. So that's a very cool talk to check out in the GPU session. And then Piccolo quantum objects. So like we've recently added like new features for doing time-dependent Hamiltonians, open systems with Lombardians, new quantum object utilities. We're kind of filtering out which ones we want to keep and which ones we want to like take from other packages. And then like a lot of the stuff we do under the hood is doing isomorphisms of states for efficiently like taking only the solver variables that we wanted to use. And there's some tricks to doing this. So like I mentioned, we're doing some ecosystem integrations. We're trying to combine with Quantum Toolbox, with other package, Quantum Optics. We're interested in the SciML ecosystem, and then MatNLP.jl, which is a nonlinear solver. We're in Julia at MIT, which is really cool. So be on the lookout for us like plugging these into our toolbox. We are like going towards version 1.0. We've been saying this for a while, but we're like really close, I think. So like we've recently done a bunch of kind of improvements to the way we do problem templates. So I showed off a couple of those in the thing. From Mintime, we have unitary problem templates, density operator problem templates. We're kind of improving these, streamlining them. We're adding ecosystem integrations. We're doing visualizations. So like this fall, we're going to be like really pushing on the documentation side and like leveraging like the multi-docs framework that kind of SciML has. Building an example library, and then adding benchmarks. We want to add benchmarks with some other solvers. We also going to then this winter work on like really digging into the solver side of things and making this like modular solver backend for MatNLP, IPOpt, and some other solvers. Work on performance improvements and get a Python front end down. I know this is not the place to use Python, but unfortunately, experimental physicists are kind of stuck in the past, but we hope that this is a backend in Julia. They'll actually start to use Julia as well. We'll sneak it in. And then in the spring, we're gonna put the final touches on and get all of our testing pipelines very polished. Put out a white paper ideally, and like we're starting to think about like working on a custom code gen agent, because a lot of this boilerplate code we think could be automated and potentially set up in some way that would make it really easy to like go from Hamiltonian to like solving these problems. If anyone is experienced in this, please reach out to me. Yeah, so we also under an org now called Harmonix, which is also a startup that has recently raised a pre-seed. So in lieu of NSF funding, this is what we're doing. And so if you want to check out our page, we're gonna have the QR code on the next slide as well. So that QR code's right here. And just to say thank you to my PI, Andy's PI, Fred Chong. Zach is here. Zach is sadly not here this week. Andre, Dave, students who work with us, Gennady, Jack are here. They're core developers, and Aditya, who was a developer with us and kind of still hangs around. With that, I'll say thank you and open up for questions.
Yeah, thanks for a nice introduction of the package. So you mentioned that Grape is sort of like outdated, and I wondered if you could like comment on whether it's just always better to do this IPO-PT or MAT NLP, like basically this nonlinear problem optimization you do. And then in addition, like are there any, so you said you had to do more in this Piccolissimo optimize how you basically do things on the back end, I guess. Yeah, so is it more scalable to do one thing over the other?
Yeah, so I think there is a trade-off. There's definitely, in one sense, a memory trade-off. So in a indirect method, you can get away with like saying we're going to propagate forward this state and then kind of delete it and write over it or something and propagate it forward. The problem with that is this is like a classic problem in machine learning is you have this kind of vanishing gradient problem where if you propagate through a big roll, let's say you saw a long time horizon ODE, errors accumulate, your gradient information when you back propagate kind of can get accumulated errors. So what we do by leveraging like this kind of constraint between time steps, you can actually do all of these things in parallel. So you can actually parallel solve for all of these things and parallel solve for all the gradients. So you get kind of performance improvements there. You kind of have this ability. So I kind of hinted at it here, where like in the space of possibles, like the space of where the variables live, you kind of have this region that's only feasible, and that's the only place like an algorithm like Grape can live. So a direct method can hop out of this region and kind of land back in this kind of way by violating the constraints. And this is a little bit weird, but I do think from a lot of optimization perspectives, this is like better, and there's been a lot of work in robotics, and again, this is like kind of what roboticists have done to get these kind of solutions. And there's also like the way these problems are structured, I think that like in parallelness of it is super helpful. I forget if there was a second part to your question, but if that was
I guess it was more like to scalability. So right now you had a fog space of 20, I guess I saw. What do you imagine as like the upper boundary of something that's feasible?
Yeah, that's a great question. Okay, so in all of the code we showed, we were under the hood computing Hessians. So in these things, you have to compute things called like Hessians or Lagrangians. So you could get rid of that actually, and then you could go up to even higher levels and you're losing some convergence performance. Exactly where the state dimension kind of blows up to the point where you can't solve it in memory, it's gonna be at worst, like if let's say we have n time steps, we're gonna store the full state n times, order n times, while Grape maybe stores it order 1. But if n is kind of close to 1, then they're pretty comparable. Yeah, we're still exploring this and the computational complexity of this and exactly what we can fit in. The cool thing is there's a lot of interesting tricks for like reducing the state dimension that we're starting to look at. I think the biggest problem I've put on this is 6 qubits, which was is that 128 dimensions. I think we've done more. I think we have people that's done more. So this is one of the reasons we're working in performance improvements and like trying to do potentially distributed versions of this. Core,
maybe just
okay.
Like we're also like
Sorry,
it wasn't multi-threaded.
it wasn't multi.
That was a single-threaded example too.
Yes.
So like there's no scale.
We can talk about this after.
Yeah. So I think
Yeah.
probably a good idea. Any other questions? Yeah. Okay. We maybe don't have time for more than one. Okay, we can just thank the speaker again and take any other questions offline. Thank you guys.